Welcome back, my dear child. Now the concept that we are going to do in this particular module is called as valency. And the first thing that we need to do is we need to understand what is the definition of the term valency. Let's have a look. As far as valency is considered, valency is nothing but the combining capacity of an element. And what does this combining capacity depend upon? It depends upon the number of valence electrons which are present in an atom of the element. Which means that if I have a particular atom and I need to calculate the valency for that particular atom, I need to know the combining capacity of that atom, and for that I need the number of valence electrons. Electrons which are present in the valence shell, electrons which are present in the last shell are called as valence electrons. Okay, let's have a look at this particular concept in detail. Valency, how do we find out? First of all, the atom of an element has only one orbit. So if an atom of an element has only one orbit, if it has a single orbit, and if that orbit has exactly 2 electrons, then that particular atom is stable according to the duplet rule. I repeat, if you have an atom, if it has a single shell, and if that particular single shell is completely filled with a total of 2 electrons, then that particular atom is absolutely stable. Who's the example? Helium, given as He, my first noble gas. And if you don't want to be stable according to the duplet rule, you have the option of the octet rule. Have a look. So here we have it. Helium over here has a single shell, 2 electrons in that particular shell, so absolutely stable. However, for other noble gases, they are going to follow the octet rule. So if the atom of an element has exactly 8 electrons in the outermost orbit, then that element is stable according to the octet rule. So let us say you have a number of orbits. Who is the important orbit? The last orbit, the valence orbit. And if you have exactly 8 electrons in the valence shell, you are absolutely stable according to the octet rule. All other noble gases except helium will follow that particular rule. Apart from helium, we have neon, argon, krypton, xenon, radon. All of them are going to follow the octet rule of stability. And the problem is, apart from the 6 noble gases of helium, neon, argon, krypton, xenon, radon, all other elements in the entire periodic table are unstable. And to gain stability, to gain the electronic configuration of a noble gas, they will be having 2 options. Either they will transfer of electrons or they will share electrons, which will lead to the formation of bonds. Let's have a look over here. So as far as valency is considered, element can attain stability in 2 ways. As I said, first one, transfer of electrons. Second one, sharing of electrons. First one, transfer of electrons. Second one, sharing of electron. And whenever you have transfer of electrons, a bond is formed called as an electrovalent bond, which you can also call as an ionic bond, and sharing of electrons, from there you're going to have a covalent bond, right? Okay. Now valency of some elements. We're going to calculate the valency of the first 20 elements. Listen to this very, very carefully. Okay. So my first element is going to be hydrogen, has an atomic number of 1, has an electronic configuration of 1, has valence electrons 1. What is the desired configuration for hydrogen? Hydrogen wants to be like helium. So for that, it will require to gain 1 valence electron. In that particular case, the valency could be -1. Hydrogen also has an option of losing an electron. If it does that, it will have a valency of +1. Next we have helium, atomic number 2, electronic configuration 2, number of valence electrons 2, but it is stable according to the duplet rule. So the valency is absolutely 0. It doesn't really need to do anything. Lithium, atomic number 3, configuration 2, 1, has 1 valence electron. If it loses that 1 valence electron, it will get the configuration of helium. It will become stable. You lose an electron, you yourself become positive. How much positive? +1. Beryllium, atomic number 4, configuration 2, 2. It has 2 valence electrons. If it loses those 2 valence electrons, it will get the configuration of helium again. Lose 2 negatively charged electrons, you yourself have valency of +2. Boron, atomic number 5, configuration 2, 3. If it loses those 3 valence electrons, it is going to have a total of 3 positive charges, and it will get the nearest noble gas configuration of helium once again. Now, carbon, slightly different rules. Carbon over here has an atomic number of 6, configuration of 2, 4, has 4 valence electrons. technically speaking, it can lose 4 valence electrons, it can also gain 4 valence electrons. It prefers to gain in most of the cases, and it forms an ion called as carbide. But carbon also has an option of sharing valence electrons, and therefore for sharing of valence electrons, I'll say the configuration is 2, 4 and the valency is exactly 4. Okay. Nitrogen, atomic number 7, configuration 2, 5, desired configuration 2, 8. For that it needs 3 electrons, gains 3 negatively charged electrons, has a valency of -3. Oxygen, atomic number 8, configuration 2, 6, desired configuration 2, 8. Whose configuration is that? Neon. Gains 2 valence electrons, has a configuration of 2, 8 then, and has a valency of -2. Fluorine, F, atomic number 9, configuration 2, 7, has 7 valence electrons. 2, 7 wants to become 2, 8, requires a single valence electron for that, gains it, becomes -1. And finally we have neon, atomic number 10, configuration 2, 8, has exactly 8 electrons in the last shell, is absolutely stable according to the octet rule. In fact, carbon, nitrogen, oxygen, fluorine, everybody was trying to become neon till now, correct? Sodium has an atomic number of 11, configuration of 281, loses an electron to become neon 28, and therefore has a +1 charge because it loses one negatively charged electron, so itself becomes +1. Magnesium, atomic number 12, configuration 282, loses 2 valence electrons, has the configuration of neon, has a charge of +2. Aluminium, atomic number 13, configuration 283, loses 3 valence electrons and has a charge of +3, again gains the configuration of neon. Silicon, it is 14, 284. So in this particular case, 4 valence electrons, has 2 options, loses 4, gains 4, but it prefers to share 4 electrons in most of the cases, so the valency is 4. Okay, who do we have next? Phosphorus, atomic number 15, configuration 285, desired configuration 288, that's the configuration of argon, gains 3 electrons, has a valency of -3. Then we have, after phosphorus, we have sulfur, we have S, atomic number 16, configuration 286, desired configuration 288, requires 2 valence electrons, gains them, has a valency of -2. Chlorine, atomic number 17, configuration 287, has 7 valence electrons, 287, wants to become 288, wants to get the configuration of argon, gains 1 valence electron to become -1. That's the one we were looking for actually, you know. Argon, atomic number 18, configuration 288, absolutely stable according to the octet rule, has 8 electrons in the last shell. So 0 valency, neither loses nor gains electrons. Potassium, atomic number 19, configuration 2881, it will have to lose 1 valence electron to become like argon, has a valency of +1. And finally we have calcium, atomic number 20, configuration 2882, loses 2 valence electrons, gets a charge of +2, right? So that is how you calculate the valency of the first 20 elements of the periodic table, that easily. Okay. Now there's a concept called as variable valency. A single element, if it exhibits more than 1 valency at a particular time, it's called as variable valency. Always the lower valency has a suffix of us and the higher valency has a suffix of ik. What do I mean by that? Copper, lower valency +1, higher valency +2. So it is cuprous and cupric. Iron, ferrous and ferric with respect to +2 and +3. Mercurous and mercuric, +1 and +2. Plumbous and plumbic with respect to +2 and +4. Tin, stannous and stannic with respect to again +2 and +4. So always the lower valency is us, for example cuprous, ferrous, mercurous. Higher valency is ik, for example cupric, ferric, mercuric respectively, right? Okay. Now formation of sodium chloride, the last particular concept for this particular module. Let's have a look. Sodium will have to lose 1 electron from the outermost shell to attain a stable electronic configuration of neon. Why do I say that? Sodium has an atomic number of 11, configuration 281. Stable or unstable? Unstable. To gain stability, it needs to lose 1 valence electron, and when it does that, the new configuration is going to become 28, which is the configuration of neon, correct? Chlorine, on the other hand, atomic number 17, configuration 287, desired configuration 288. That's the nearest noble gas, argon. For that, it needs to gain a valence electron. When you do that, you will have Na with a charge of 1 plus and Cl with a charge of 1 minus. Okay. So, chlorine will have to accept 1 electron to attain the stable electronic configuration of argon. Continuing to the orbital diagram, let us have some fun. Have a look. So, there we have it, sodium atom, chlorine atom, 281, 287 respectively, both unstable. Sodium needs to lose 1 valence electron, chlorine needs to gain 1 valence electron. The electron which sodium loses is the same electron that chlorine will gain. Effectively, there is a transfer of electron from sodium to chlorine, from metal to non-metal, from electropositive to electronegative elements, right? So, when we make that structure again, this particular time what are we going to do? We are going to shift the electron of sodium. That's there, we did it. Now, that particular orbit, the M orbit, it does not have any electrons, so we are going to make it vanish, right? Now, I will get Na with a charge of 1 plus, Cl with a charge of 1 minus. Those are the charges developed. And what does that give me? It gives me sodium chloride given by the formula NaCl.